In examining and creating a heating curve for water, or any substance, usually you'll see temperature in degrees Celsius on the y-axis. Occasionally it could be Kelvin, and energy on the x-axis, oftentimes in kilojoules, though regular joules and calories are okay too. You'll find two important notches on the y-axis. For water, that'll be 0 and 100, which represent the melting point and the boiling point. Under normal pressure conditions, water is a solid under 0 degrees. So if you add energy to, say, very, very cold ice, it'll stay ice or stay solid until it reaches 0 degrees. So this line here represents the internal increase in temperature of that ice as you add more energy until it reaches 0 degrees, at which case it'll begin to melt, which we're going to label this line or this phase change as fusion, which is the solid to liquid transition. Adding even more energy will eventually have it so that there is no more solid left and you have just liquid, and that liquid is getting warmer. And the liquid will continue to increase its internal temperature until it begins to boil. And we're going to label this line vaporization, vapor for short. And this is the liquid to gas transition. After all the liquid is gone and it's just gas, then you're heating the gas. This heating curve is not to scale. The vaporization line should be quite long because it takes a lot of energy to turn a liquid into a gas, or as you know, it takes a lot of energy to boil water. The first plateau of the heating curve is the melting point, and the second plateau of the heating curve is the normal boiling point. Melting and freezing are just opposite processes, so you guys know that water melts at 0 degrees and it freezes at 0 degrees. It depends on the direction. Because this is a heating curve, we're moving from left to right, so we're talking about melting and boiling as more energy is added endothermically. I have broken the heating curve into 5 sections: solid, melting, liquid, boiling, and gas. I'm going to zoom in on the solid section and draw a molecular level type of diagram that represents really the packed molecules as ice. In the second section, the ice has started to melt, so it's ice sitting in a puddle of water. In the third section, I've got just liquid that is heating, so I'm going to draw a pot, and inside this pot is just water. So this is like you've gotten water out of the sink and it came out at 20 degrees, and it's going from 20 to 30 to 40 to 50 to 60 to 70 to 80 degrees, then even 90, and at 100 degrees it begins to boil. So we've got water that has those little characteristic bubbling little circles in it, and this represents the steam or the water vapor that is coming off of that pot of water. And this happens at 100 degrees. So when you're boiling water, the temperature of water will remain constant at 100 degrees because all the extra energy you're adding is going into breaking intermolecular forces, which are those forces that hold those molecules together in the liquid state. And they've all got to be overcome in order to break something out of the liquid state into the gaseous state. And then the fifth section, I'm going to draw water that is confined in a three-dimensional space, such as a box. And those little water molecules are going to have a certain amount of average velocity and kinetic energy. They are moving relatively quickly compared to liquid and solid. Q equals mc delta T can only be used at section 1, section 3, and section 5, where there is a solid, liquid, or gas phase that is not changing from one phase to the next. It is simply heating. And the reason that you can use Q equals mc delta T for only sections 1, 3, and 5 when it's a solid, liquid, or a gas is because there is a change in temperature, which is represented by the slope. You cannot use Q equals mc delta T at sections 2 and 4 because there is no change in temperature. So there are two values that you can either look up or be given, and they are called the heat of fusion and the heat of vaporization, or delta H fuse and delta H vap. The heat of fusion is going to usually be represented in kilojoules per mole. Effectively, it says how much energy in kilojoules is needed to melt 1 mole of a substance. It's negative for the freezing from liquid to solid. So they are the same value, they just have opposite directions. Energy goes in to melt, energy comes out to freeze. For the vaporization of water, you will be given a numerical value that is delta H VAP, which also may be usually in the units of kilojoules per mole. However, any unit that is heat per amount is okay. It could be calories per gram, it could be joules per mole, it could be kilojoules per gram, whatever the situation is. But if you look at the equation, the most common way you'll see the amount of heat expressed is the delta H, and then this part right here will be delta H fusion or vaporization. But there are two alternatives. It could also be condensation or solidification. Solidification is the opposite of fusion, and vaporization is the opposite of condensation. They will have opposite signs. For water, the heat of fusion is approximately 6.01, and that would be 6.01 kilojoules per mole. However, heats of fusion can be represented in any heat per amount unit, such as calories per gram. The heat of vaporization for water is 40.7. So as you can see, it takes a lot more energy to vaporize 1 mole of water than it takes to melt 1 mole of water. My opinion on heat of fusion and heat of vaporization, and of course heat of condensation and solidification, which are the opposites, is to simply set up a ratio. Here's an example of how to use the concept of using a ratio or a proportion when you cannot use Q equals mc delta T. This question asks, how much energy is needed to vaporize 50.0 grams of water at 100 degrees Celsius? One of the biggest pitfalls students make is they see this 100 degrees Celsius and they think, oh, that's my delta T, I'm going to plug it into Q equals mc delta T, and there you go. That is incorrect. If you see the preposition at, and then you see a temperature, that usually indicates that it's at the boiling or melting point, and you don't use that temperature in your math. It's extra information. We all know that water boils at 100 degrees Celsius. If it didn't say that, it would not change our problem at all. So here's how I will proceed. Take your amount of water and check to see if it is in moles already. And remember, this does not have to just be for water. It could be about ammonia or neon or anything. If you're given the heat of whatever, heat of fusion, vaporization, condensation, solidification, even combustion, this trick about using the ratio will help you. Look carefully at your units. You have kilojoules per mole. It's asking how much energy, and it makes sense to provide that answer in kilojoules, is required to vaporize 50 grams of water, but notice how your proportion has moles. Occasionally, you might have grams in your proportion. I will start off with 50 50.0 grams of water, and I'll put that over 1. And if I look at my units, I'm going to go from grams of water to moles of water. The molar mass of water is about 18, and your grams of water are going to cancel out top and bottom. If you stopped the problem right now, you would have how many moles of water 50.0 grams of water is. But this question is asking you how much energy is required to vaporize 50.0 grams of water. So look at your units of moles and get rid of them by putting them at the bottom. For water, the heat of vaporization is 40.7 kilojoules. If you look carefully, you do already have a ratio right here, kilojoules in moles. At this point, put your 40.7 kilojoules, because that's how much energy is required to vaporize 1 mole of water. And the answer will be 113 kilojoules of energy are required to vaporize 50 grams of water at 100 degrees Celsius. Notice how I did not use 100 degrees Celsius in my equation. I can't use Q equals mc delta T. Here is the fail that some students will make. Do not do what I'm writing in red. So some students will see Q equals mc delta T as the only equation they seem to remember from thermochemistry, the only thing they can remember on what to do. And then they start plugging things in. Well, they remember at least that Q is heat. The mass, oh, I've got that. That's 50.0. The specific heat capacity of water is not provided here. It is 4.184 joules per mole degree Kelvin. But sometimes people forget what C means and they'll just plug in whatever they see. Maybe 40.7 should go there. And then they plug in the 100. Notice, remember, that delta means change in temperature. This is not a change in temperature. This is at 100 degrees Celsius. So you cannot use this equation at all. So back on my heating curve, I'll put a 2 and a 4 for when you have to use the heat of a phase change ratio to solve for the amount of heat. That is all there is for heating curves for water and how to distinguish between when you can use Q equals mc delta T and when you can't.